currently Professor of Computer Science in the Department of Electronics and Computer Engineering at IIT Roorkee. I'll be taking this course on operating systems. Operating systems is a basic course for all CSE programs, and it is one of the most important essential courses in the program. There are a number of books on operating systems written by very well-known authors. Let's have a look at those books and the names. First and foremost, the book by A.S. Tannenbaum on modern operating systems. This is considered to be the Bible of all operating system courses. Then we have a book by Silbersash and Galvin, which is operating system concepts, from which there are important parts to be taken. For the Unix operating system, we shall talk of Maurice Back. For a design-oriented approach, we have the book by Crawley. And finally, the book by Stallings is also an important book on operating systems. So these will be our 5 references for this course. Now let us introduce ourselves to operating systems. All of us have seen how what an operating system does. When we switch on the computer, the first thing that comes on the screen is the operating system. We have seen Linux, we have seen Unix, we have seen Windows. Among Windows there is XP, there is Windows 2000. So the first thing that talks to you when you switch on the computer is the operating system. Today, no computer works without operating systems. So what is an operating system? An operating system is a software which controls all of the computer's resources, and it provides the base upon which applications can be written. It is a system software which provides an interface between the user and the system. When I say system software, it means it's not an application software. What the user writes is an application, and what the manufacturer provides is the system software. So there is a difference between system software and application software, and we shall presently see what the difference is. But first let us go to the other aspects of an operating system. An operating system can also be said to be an extended or virtual machine, because it shields the programmer from the disk hardware and presents a simple file-oriented interface to the user. It also conceals or hides from the user all the unpleasant business concerning interrupts, timers, memory management, file management, etc. The operating system is also a resource manager, as I mentioned earlier. There are 4 resources in a computer system. We have the process or processors, we have memory, we have I/O devices, and we have files. These are the 4 resources in a computer system, and it is the operating system which provides an orderly and controlled allocation of all these resources in the system. Hence, the operating system contains a processor manager, a memory manager, a device manager, and a file manager. Now, what is the purpose of an operating system? As I said earlier, the operating system provides an environment in which programs can be executed. You cannot use the computer unless you have an operating system, because when you want to write a program, when you want to run it, when you want to compile it, you always need an operating system and commands from the operating system. So the operating system provides an environment in which programs can be executed. It makes efficient use of the computer hardware and the peripherals. It hides the peculiarities of the disks and other I/O devices and presents the user with a nice, clean, abstract model of the devices. Now let's look at the hierarchy of computer system software. If you look at the diagram, you have the physical devices or the hardware at the bottom. That is the hardware, that is the computer, the memory, the I/O devices, etc. Over and above that, we have the microprogramming layer or the machine language layer. This is an abstract layer, and over this we have, as shown in the diagram, we have 6 or 7 parts. We shall talk of these in detail later on, but these 2 levels just above the physical devices is the actual operating system. We have the FLIH, or the first level interrupt handler, we have the dispatcher, the inter-process communication system, the program or the process manager, memory manager, device manager, and the file manager. So these 2 layers form the operating system, and this is an essential system software. All of this, the whole diagram is a system software, but the first 2 layers are essential to any computer system. Above that, we have 3 more layers. These are desirable system software. If they are present in the system, it is good, it helps us, but if they are not present, we can still work the hardware. So we have the compiler, the editor, the assembler, the command interpreter, etc. for writing the program, for compiling the program. And then over and above that, we have the error tools, the debugger. So if there's a bug in the program, you can debug it using this software. We have certain PC tools that help us to make the system more efficient, and there is a library of files, the DLLs, etc. Finally, the top layer is the application layer, where you can do anything. You can have a database management system, or you can play games, or you can have some other user utilities. So this is the total system software, and the operating system lies in between the physical device and the higher layers. We look at the history of operating systems. The operating systems of today are very complex, highly sophisticated system software running into thousands and thousands of lines of code. But you'll be surprised to know that earlier systems, the beginning when computers were first built, had actually no operating systems. So today we talk of Windows operating systems, which is one of the most popular operating systems by Microsoft. We also talk of Linux, we talk of Unix, and there are other smaller operating systems by Mac, like Mac, etc. But let's look at this brief history of the operating system, and let us go by generations of computers, the period of that generation, the operating system used at that time, and the characteristic features of use by the operating system. Generation number 1 went from the period 1945 to 1955. That was the time of the ENIAC and the EDSAC machines, which were basically analog computers, and in fact there was no operating system used in those computers. And so how was the program written? It was actually not written, but it was jumper wired onto plug-in boards. Whatever we wanted to do would have, the jumpers were set, and then those jumper boards were put into the computer. So every time you wanted to change the program, you had to wire that plug-in board all over again. It was a lot of work, and therefore the applications that were written were very simple and very small. But then came the generation number 2, from the period 1955 to 1965. That was the time of the IBM machine. And that is when IBM actually came into its own. Most of us remember the IBM 1401 and later on the IBM 7094. The operating systems that were used for these machines are called batch operating systems. Batch operating systems mean that programs were not interactive. So whoever wanted to use the computer would bring his or her program to the computer center, and each program would be run one after the other. So it was like a batch. One after the other, the programs would be run. These were not interactive operating systems, but batch. These operating systems used paper tape as the input. The program was punched onto the paper tape, and there were paper tape readers which read those punched paper tapes and sent the data or the input program into the computer. It was also possible in these operating systems to print the output offline. You could not print it online like we do today. Moving on to the generation number 3, from the period 1965 to 1980, one of the most common and popular machines, the IBM 360, was developed in those days, and for the first time operating systems came into their own with this machine. These were time-sharing operating systems. Unlike batch systems, they were time-sharing, so 2 or more people could use the system at a time. Many programs could run on the machine at the same time. This was also the time when the mini computers were developed, and the most famous of them is the PDP-11, which ran from PDP-1 to PDP-11. There were generations of these machines. The concept of spooling or online printing came into its own. We shall discuss these in more detail later on. And more importantly, multi-programming. So because these were time-sharing machines, we could use multiple programs, or we could run multiple programs on the computer for the first time. These were large and complex operating systems. There were many bugs, and therefore there had to be many releases of that operating system. Next came the generation 4 machines from 1980 to 1990, and we saw these were also used with the IBM 360, and for the first time we saw the MS-DOS operating system. The MS-DOS operating system, which is a disk operating systems, this was a time when disks started appearing, floppy disks as we know them. They were large floppy disks in the beginning, 8.5-inch size, which then reduced to 5 3/4 and then 3 and 1.25 inches. And now, of course, we don't have disks, we only have CD-ROMs, etc. It was also the time when Unix operating system became popular. Later on, we shall see a comparison between Windows and Unix operating systems. The most important characteristic of these operating systems was, or still is, that they are user-friendly. So it was easy for the user to interact with the computer using this operating system. So the term user-friendly first started with these operating systems, MS-DOS and Unix. In fact, the user need not be a computer professional. He would not have to know anything about computers in order to run the computer. This was a big help, and therefore the operating system did all the work. The programmer or the user just had to put his program into the system. The era from 1990 is known as the 5th generation of computers, and we are still in that era, and these are now what are known as KBCS, or knowledge-based computer systems. And we have networks, we have distributed systems. So as computers started being put together or connected together, the operating system had to undergo changes to incorporate that connectivity. So we have network operating systems and distributed operating systems. Now, there are 2 people who are considered to be the fathers of operating systems. These names are most important in the study of operating systems. We should not forget E.W. Dijkstra and Per Brink Hansen for whenever we talk of operating systems. Having given an introduction to operating systems and how they developed, let us look at the concepts, the 2 main concepts of operating systems. Operating systems actually manage 2 software objects. These are processes and files. So a process and a file are the 2 software objects managed by operating systems. And these are implemented in the operating system by making use of what are called system calls. System calls are nothing but extended instructions. We now look at the two basic concepts in operating systems. These are processes and files. These are the two software objects which are managed by the operating system. Most basic entities in the operating system are processes and files. And these are implemented by complex instructions, also called extended instructions, by what is known as the use of system calls. We shall talk about system calls in more detail later on, but for now we should see what these systems are, what a process is and what is a file. Looking at processes first. What is a process and how is it different from a program? We know that users write programs in some source language like BASIC or C or C++. So when a program is written, that is a program. When you write a sequence of steps, that is a program. But when that program executes inside the computer, it becomes a process. So a process is a program in execution, and every process has an identity or an ID. And in a multitasking or multiprocessing system, when a process or program runs, when multiple processes run, it is actually a kind of mirage. In the real sense, only one process is running. So there's only one program in execution. The others are in either a saved state or in a restored state or whatever. So when one process runs and then it has to go off the system and another process has to start running, then the context of that process has to be saved. So when the process runs, its context is restored. When it goes off the computer, its context is saved. And by context of a process, we mean its data, its memory, its stack, the program counter, the registers, the actual codes, etc. The different calls, system calls that are used for managing processes in a operating system are for example, creating the process. You can block a process, you can terminate a process, you can request for memory, you can fork a process, or the process can release memory, etc. In a multitasking system, therefore, as I said, there are many system calls for creating, blocking, terminating, and requesting for memory, etc. We have two kinds of operating systems. They could be multitasking systems or multi-programming systems. Most of today's operating systems are multitasking, but the other word, actually these two words are synonymous. Multitasking is the same as multi-programming. Other than the process, we have what are called files. All of us know files. A file is the program where you store it. When you store a program, it becomes a file. And as similar to programs or processes, we also have system calls for files, and these are for creating a file, for deleting it, for renaming it, for reading a file, for opening it, for writing, etc. All of us have done these operations. We have created files. Files are different from processes in the sense that a file need not be always an executable file. A file can be a database file, it could be simply a text file, whereas a program or a process is always a executable file. Now most operating systems have the shell. You've heard of the Unix shell. The shell is a command interpreter. All these system calls for, or the commands that we give for creating or deleting files or for creating and deleting processes, they are interpreted by the shell. So the shell is a command interpreter. It is actually not part of the operating system, but it uses its features extensively, and it gives you a good example of how system calls can be used. Now let us look at the process model. We can give an analogy with how a secretary works. Let's assume that the process is a secretary in an office, a secretary to the boss of the office, to the head of the department or whatever. Now the secretary does various jobs. So he or she is in various states. For example, she may be typing at one time, at another time she may be looking at some file, she may be also answering the telephone. She has a number of jobs to do. So if we say that the computer is the secretary, then the computer does a number of processes. So a multitasking computer can be seen to be like a secretary who has many jobs to do. And therefore, like a secretary, the process may be in various states. In this diagram, I have shown 3 states: the running state, the blocked state, and the ready state. The arrows show the transition between the different states. The process, for example, that is using the computer is said to be in the running state. The program is running. So for example, the secretary is typing. Now while the secretary is typing, suppose the phone rings, the telephone rings. So the secretary must stop typing. She must make a mental note of where she was typing, and then she must listen to the telephone. In a similar manner, when a process is running, it might need some input-output. So it stops for a moment, blocks itself. Then it does whatever it has to do, and it becomes ready again. It is ready to start running. Similarly, the secretary would listen to the telephone call, answer the telephone call, and then go back she was typing. So the analogy with the secretary is like that of a computer which has with a process which has many states in which it can run, it can be present at any time. In this diagram, transition number 1 shows that the process is blocking for input. Some kind of input is required, so it stops running, it goes into the blocked state. Then there is a operating system program called the scheduler, which we shall study later. It is the job of the scheduler to pick up another process. There are many processes which are in the ready state inside the computer. One of the process runs and the others are all ready to run. So as soon as the running process blocks, the scheduler will pick up another ready process and put it onto the computer. So that process becomes runnable. Now as soon as the input becomes available, the computer or the process goes back to its state. Now the basic building block of an operating system is the kernel, nucleus, which we saw in the diagram that we saw in the beginning. The first 3 parts of the operating system are called the kernel, and this kernel it's called a kernel because it is the nucleus of the operating system. It has various functions to perform. These are major functions of the operating system. The kernel implements processes. So all the processes that are currently running or ready in the system are implemented inside the kernel or nucleus. Whenever a process goes from ready to blocked, or from blocked to ready, or from ready to running, then it is said to be dispatched. Process dispatching is another function of the kernel. Now when there are multiple processes inside the computer, these processes need to communicate with each other. This is called inter-process communication, and all kinds of inter-process communication is handled by the kernel. And finally, one of the most important jobs of the kernel is to handle interrupts. The user doesn't know this. In fact, the user is not aware that every time we type a key on the keyboard, the system is interrupted. So you can imagine that when you're typing something very fast, every key that you press gives an interrupt. Every time you click a mouse, there's an interrupt. So all the time while programs are running, there are hundreds and thousands of interrupts happening inside the computer. And all this is so fast, actually the processor is so fast that you don't feel that it is doing so many jobs, but actually the processor is doing a number of jobs at a time. The computer system is doing a lot of jobs at a time, and each job is started or interrupted. So there are a number of interrupts inside the computer, and this job of interrupt handling, of knowing what to do when a particular interrupt occurs, is done by the kernel. So we've seen processes and we've seen files. We've given a brief introduction. We shall look at processes and files in more detail later on. Here let us see a simple way in which a process is implemented in the computer or by the operating system. Since there are a number of processes, all information about a process is kept inside what is called a process table. So if there are n processes inside a computer, there will be n such process tables, and each of these tables is actually a linked list. Those of you who know programming know what a linked list is, and the various fields in a linked list. So a process table consists of the information of every process, and each of these tables is linked with another. So it is a data structure having various fields. This has one entry for every process, and each entry for every process is partitioned into 4 sections, one each for PM, that is process management, one for memory management, one for device management, and one for file management. So whatever processor the process uses, whatever memory it uses, whatever device it uses, or whatever files it uses, all the 4 resources that the process uses, all information about its usage is kept in this process table. When we say that there are 4 sections of the process table, let us look at what are the contents of that process table. We look at the process management table first. In this we keep an account of all the registers, the CPU registers that the process is using and what are their contents. The value of the program counter, which points to the next instruction that has to be executed, is kept in the one field. Then we have the program status word, and we have the stack pointer. Similarly, in the memory management segment of the process table, we have a pointer to its text segment. We might have a pointer to one of the data structures that is being used, and we might have some information about the exit status of the process. Similarly, in its file management portion, we would say what is the root directory for that particular file, what is its working directory, and what are the other file descriptors that are being used. Continuing with the same thing, we shall also note the state of the process. So whether it is running, or it is suspended, or it is blocked, or it is ready. So the state of the process. Then the operating system also keeps account of how much time the process has used the CPU. There's a field for process identity and the various flags that are used by the process. Similarly, for the memory management portion of the process table, we might have information about the parent process, what is the ID of the parent process, what is the effective user ID of the process, and other flag bits. For the file management portion also, we might have some system call parameters, an effective UID, and file bits. Every I/O device class, whether it is a floppy or whether it is a hard disk, whether it's a timer, a printer, terminal, nowadays there are so many I/O devices or devices that can be used with the computer. Every one of these devices has a process associated with it. This is of course a system process, because these are part of the operating system. We have heard of drivers. So every I/O has a driver associated with it, which is a software which we shall discuss later on, and a location near the bottom of memory which is called the interrupt vector, and this interrupt vector contains the addresses of all the interrupt service subroutines. As I said, every device, whenever we want to start the device, there is an interrupt associated with it, and that interrupt has a service subroutine associated with it which tells the operating system what that particular device does. Now let us take a scenario where we have a process P1, let us say it is running. The process P1 is running and doing whatever it has to do, and if a disk interrupt occurs, that means if the process wants to read or write into the disk, then that application process P1 must stop running and the disk process must start. Whenever you want to read a disk, the disk read process starts, and therefore an interrupt takes place, and that interrupt interrupts the process P1 from running. So process P1 goes to the blocked state and the disk process becomes ready to run. The first thing that happens is that the hardware will push the program counter, the program status word of the process onto the stack so that it remembers where to start back. The program counter always points to the next instruction, and therefore once the program starts running again, it must start running from where it left off. Therefore the program counter value is saved and the process status word is also saved onto the stack, and this is done by the interrupt handler. This portion is provided by the interrupt handler and automatically done by the hardware. A new value of the program counter is loaded into the program counter from the interrupt vector, and then after that all the registers of the previous process are saved and a new stack is set up for the new process. These two functions are provided by the assembly language program. Then the service process, the interrupt service process, that is the disk process in our case, starts running after it is made ready by the C procedure. So what we are saying is that the hardware comes into play, the assembly language portion comes into play, and the C program also. So the part of the operating system which directly controls the hardware, which is part of the assembly language, and also C language or whatever high level language the operating system is written in, all those will play a part in implementing the process. Finally, when the process is marked ready, then the scheduler will decide which process is to run. As I said earlier, the scheduler is a system program which picks up one process to run from among the many processes that are ready to run. And when that process is picked up, then the C procedure will return to the assembly language program of that particular process, and the assembly language program will start the current process running. So this is in brief the what happens inside the computer, or what is done by the operating system when one process has to interrupt itself because it has to do a disk read. We shall deal with this in more detail in the chapter on disk and I/O management. This is only a brief introduction to what are the complexities that go inside the computer and how these are handled by the operating system. So this is how the operating system functions whenever there is an interrupt. And as I said, there are so many interrupts in the system. Every time you press a key, there's an interrupt. All these functions have to take place inside the operating system every time there is a interrupt like this. So you can see how complex it is inside, but all this is hidden from the user, and the user doesn't get to know about all this at all. So having had a brief idea of what goes inside the operating system kernel and what is the function of the file and the process, let us now go to a very important concept in operating systems, which is inter-process communication, or IPC as it is called. Processes frequently communicate with each other without interrupts. We've seen interrupts, but it is not necessary that when there is communication between processes, there should be an interrupt. An interrupt normally happens when the user presses a key or when there is some disk reading or writing to be done. But normally processes would communicate with each other. For example, if a user process wants to read from a file, then the file process will tell the disk process, and the disk process will send the file to the file process, and then the file process will send this file to the user process, and so on. There is a lot of communication between processes, between the internal processes inside the operating system. Such communication takes place without interrupts. But there are many problems with that. Might sound simple, but there are many problems with such a kind of IPC, or inter-process communication. Let us take a simple example where we have two processes, PA and PB, who both want to write to a printer. There is a printer attached to the system, and two processes are running. They are sharing the printer. There is a printer spooler. Spooler is a program which actually keeps track of which process wants to print the file, and this is does by having a directory. A directory is simply something which notes down all the processes, just like any other directory that we know in real life. So there is a printer spooler which uses a spooler directory, and when a process wants to print a file, it writes its name into the spooler directory. There are two global variables, in and out, and these point to the next free slot in the directory and the name of the next file to print. So in points to the next free slot in the directory, and out points to the next file that has to be printed. Now let us say process PA is running first, and let us see, this diagram shows the actual scenario. We have the program PA running, and we have the in which has 7, which means 7, in is pointing to the next free space in the directory, and out is pointing to the file that has to be printed. So if process PA runs first, it reads the value in equal to 7, it puts 7 in its local variable and immediately gets taken off from the computer. For some reason it is taken off the computer before it has actually incremented the value of in. Because in is 7, it notes the value of 7 in its local variable in its own program, but before it can increment the value of in so that in becomes 8, because it should point to the next free slot, it gets taken off from the computer because another process PB has to run. Now when PB runs, it also reads the value in equal to 7, which is actually wrong. It should have been 8, but it reads in as 7 because in has not been incremented by PA, and it puts its file name in slot 7 of the directory. It increments in make it 8 and then gets off the computer. So its turn is off. Now PA will run again, but when PA runs, its own local variable has 7, so it rewrites slot 7 with its own file name, which means that the file name written by PB gets overwritten. Hence PB's file never gets printed. So this is what is shown in this diagram. There is the process PA and the process PB. When PA runs, the value of the shared variable in is 7, and the file number 4 is the file to be printed next. PA will put its own value in slot number 7, but before it can increment it to 8, it gets off. When PB starts running, it will also see in as 7 and it will write its name in 7. So this is a big problem. Depending on which process runs first, it is possible that there is a race between the two processes and one of the files doesn't get printed. What we mean to say is that there has to be a certain exclusion so that one file cannot rewrite on another file's space. So one of the major problems with inter-process communication is known as the race condition, which leads to what is also known as mutual exclusion. We shall talk of mutual exclusion in a little while from now. A race condition, which is the foremost problem in inter-process communication, is a situation where two or more processes are reading or writing some shared data. In the example that we took, there were these two shared variables in and out, and the final result depends on who runs when. Ideally, they should not interact with each other. They should not write on that same shared data together. If one is writing, the other should be excluded from writing onto that shared data. This is what we call mutual exclusion. Both these processes should act in a mutually exclusive manner. Otherwise, the final result will depend on who runs when, which is not what we want. Now, so what we have seen is that because the printer is a non-shareable device, the printer can be used by only one process at a time. This problem has arisen because the printer cannot be used by more than one process at a time. It is a non-shareable resource. So the other devices, for example, the CPU itself, the memory, you can read the memory, readable memory, read-only memory is shareable. Files can be read by two people two processes at a time. CPU can be shared among processes. So CPU, memory and files are shareable resources, whereas a printer is a non-shareable resource. So the first problem that arises in inter-process communication was race, leading to mutual exclusion, and we must make sure that that problem is eliminated. The second problem has to do with synchronization. Synchronization is another problem associated with inter-process communication. Normally we find that processes run asynchronously. So one process runs, then it gets taken off from the processor, another process runs, and most of the time processes do not synchronize. They do not need to synchronize with each other. As long as they do not synchronize, it is fine. But there occurs events or there occurs instances where they must synchronize each other. So we must, or the operating system must take care of process synchronization. We shall see an example where we shall show how processes must run so that they can be properly synchronized, which means that if one process is running and it wants an input from some other process, then it should stop. The other process must run. It must give that input to this first process. So there is a synchronization between the running of the two processes. This must be taken care of by the operating system. So this is the second problem. And the third and major problem with processes, with multiple processes running, is deadlock. Like in normal real life, a deadlock is a situation where nothing can run. We have, for example, a traffic deadlock. When there are no traffic lights, you can see that at a crossing, cars are moving in opposite directions, and sometimes there is no space for the car to go forward and the other car to move in the opposite direction, so that is a deadlock. Similarly, in an operating system scenario, when no process can run because each is waiting for a resource that is held by another. In the case of the traffic jam, each car is waiting for that portion of the road which is being used by the other car. So the road is the resource, the car is the process. Here similarly we have a deadlock. If, for example, there is one process which is running and it requires the printer is a non-shareable device. This printer is being used by the other process. So, and that other process requires some resource which is being used by the first process, then neither of the two processes can run. This is a situation which is called deadlock. Now, what is the solution to these problems? In order to find the solution, because multi-programming or multitasking is one of the major functionalities of today's operating systems, so solutions had to be found for these problems. And in order to find a solution for the mutual exclusion problem, we talk of critical sections. What is the problem of mutual exclusion again? We want to make sure that if one process is using a shared variable or file, another process will be excluded from doing the same thing. So if one process is writing a file, obviously we cannot expect another process to also write the file. Here is what is required is a critical section, or what is defined as a critical section. The critical section is an abstraction. It is an abstraction as far as the operating system is concerned. It is that part of the program where shared memory is accessed. So if you have a sequence of instructions in the program, and whenever in that program or wherever in that program the program is trying to access a shared variable, that is a critical section. And the problem of mutual exclusion says that we must ensure that no two processes are ever in their critical section at the same time. So if they are not in their critical section at the same time, they will not access that shared variable, and therefore there will not be any race condition. In order to provide for such, or to take care of such critical sections, we have what are called mutual exclusion primitives. Now, to avoid races, what we need to do is to ensure that no two processes, as we've already said this, no two processes may be simultaneously in their critical section. And also we make no assumptions about the relative process speeds or the number of CPUs that are inside the system. So just because a process runs faster, it doesn't mean that it should take all the resources. Even if it's a slow process, it should be able to run properly. No process stopped outside its critical section should block any other process. Process blocking is deadlock, and therefore we've got to avoid deadlock. And finally, when we try to avoid deadlock, it is possible that we starve on a process. One of the ways in which we avoid a deadlock is to make some process wait. Okay, for example, in the traffic jam scenario, if we want to avoid a traffic jam, we might do a single laning. So we'll say, all right, one side of the cars will stop, only the other side will move. If we do that, we will have avoided deadlock, but we would have added starvation. Similarly here, we say that no process should wait arbitrarily long to enter its critical section. We made it wait for a certain time to avoid deadlock, but this should not happen for a long time, otherwise the process would be starved. So we must avoid deadlock, we must avoid mutual exclusion, we must provide for critical sections, but at the same time we must avoid starvation. Today what we've seen is multi-programming. Basically we've seen an introduction to operating systems, we've seen their history, and we've seen one of the most important functions of the operating system, which is the kernel. The kernel provides for many of the important functionalities of the operating system. We've seen processes and files, and we've seen that there are many problems with processes communicating with each other. We've dealt with deadlock, we've talked of starvation, we've talked of mutual exclusion, and we've talked of critical sections. So next time we shall see in detail how mutual exclusion can be treated or has been treated inside the operating system, and we shall see an example of the producer-consumer problem, which deals with techniques to solve this problem of inter-process communication. Thank you.